Okay, so hi, welcome to this next video in linear programming. In the previous videos, we were discussing canonical forms of linear programs, and we had mentioned that there were two advantages to being in canonical form. One was that for the basis that you were in canonical form of, it was very easy to find the corresponding basic solution. The other was that, assuming that that basic solution was also feasible, it was then possible to find even better solutions than that one, assuming that they exist. And I had only demonstrated how you find the corresponding basic solution. I didn't show how you could find an even better solution, assuming that that solution was feasible. So that's what we're going to do in this video. And we're going to do it concretely with this same linear program from the previous video. So we'll do it with an example. Now this, as we said in the previous video, is already in canonical form for the basis 3, 4, 5. That is to say that the third, fourth, and fifth components of this vector C are zeros, and the third, fourth, and fifth columns of this matrix A form the identity matrix. So that's what it means to be in canonical form for this basis 3, 4, 5. In the previous video, we had said, okay, now let's pick a new basis, and we said the basis 1, 2, 4, for instance, and now let's put it in canonical form for that basis. But I don't want to do that in this video. In this video, we're going to just stick with the basis 3, 4, 5. Now, how do you find the corresponding basic solution? Well, you take zeros for the non-basic components. So in other words, so x bar will represent the basic solution. So the non-basic components of x bar will all be zeros, and the basic components are they're explicitly determined by this vector b, little b here. That's what this vector is. So this is 6, 10, 4. Now, that's because the basic columns of this matrix A, the third, fourth, and fifth columns, form the identity matrix. That's why we take the basic components of this vector x bar to be 6, 10, and 4. Now, so this is called the basic solution. It's basic feasible because it's also feasible. That is to say that all the components of this vector x bar, 0, 0, 6, 10, 4, they're all non-negative. So of course they satisfy this matrix equality constraints, because by definition that's what a basic solution does. But it's not guaranteed that it's also non-negative. But in this case it is. And so therefore it satisfies all the constraints, and so therefore it's feasible. And so we call it a basic feasible solution. And correspondingly, this basis, which gave rise to this basic solution, is called a feasible basis. Okay, so what we're going to do in this video is, now that we have a basic feasible solution, we're going to get an even better solution based off of it. And so here's how we're going to do that. Let's take a look at what results when you plug this in. This basic solution. Basic feasible solution into the objective function. We get C transpose x bar. And what I'm going to do is I'm going to break this up into the basic components and the non-basic components. So like this. C transpose B x bar B plus C transpose N x bar N. And so, I mean, I'm just rearranging the order that these terms come in. So the basic components, as we know, are C1 x1 plus C2 x2 plus... No, I'm sorry, what am I doing? It's 3, 4, and 5. Those are the basic components. It's C3 x3 plus C4 x4 plus C5 x5. Those are the basic components. And then plus the non-basic components, which are C1 x1 plus C2 x2. And let me put bars over all the x's, just to emphasize these are the components of the basic feasible solution. Okay, and now what's the point of writing it like this? Well, what I want to point out is, in the previous video, the advantage of having there was two conditions. One, for canonical forms. One, we wanted the basic indices of the basic columns of A to be the identity matrix. And the reason that was helpful is because it helped us find the basic feasible, or at least the basic solution. which it turned out to be exactly zeros for the non-basic indices, and then b for the non-basic, little b for the non-basic, for the basic components. It was still mysterious, though, why we wanted zeros for the C components, for the basic C components, that is. And it's going to become clear in this video why we wanted that. So what happens is, for this objective function, these C's are all zeros. For the basic components, the C's are zeros. And so C3 times whatever this is, C4 times whatever this is, C5 times whatever this is, these all go to 0. Because 0 times anything is 0, and then you add these zeros together and you get 0. And so that's because the reason that this part becomes 0 is because we are in canonical form for this basis B, 3, 4, 5. Now what about the other part? For the non-basic components, it's the x's actually that are zeros. The x bar n equals 0. So these x's are zeros. And then, so again, whatever the coefficients in front are anything times 0 is 0, and so so this turns out to be 0 as well. And so when you sum these two zeros together, what I get is 0. So the overall objective function is actually 0 when you plug in the basic feasible solution, assuming there's no constant attached onto the end, which is the case in this case. There's no constant. Okay. Now, so just to reiterate, there's two parts. There's the basic components, and then there's the non-basic components. For the basic components, it's because of the C's that we get 0 here. For the non-basic components, it's because of the X's that we get zeros. But in both cases, we end up with zeros, and so the overall thing sums to 0. And okay, so what we're going to recognize now is that for the non-basic components, for the basic components, 3, 4, and 5, for the basic components, the C's are zeros. So no matter what I take the X's to be, it doesn't matter, because the coefficients in front are zeros, and so the objective function won't change. On the other hand, the C's in front of here don't need to be 0. Maybe they are, but they don't have to be. And in this case, in fact, they're not. They're both positive numbers, in fact, 2 and 3. And so, because of that, if we toggle, let's say we take x1 and we start. Let's say we take a new solution and we start where we increase this x1. Well, if you increase x1, what's going to happen is, because the c1 in front is positive, the overall objective function is going to go up. And in fact, that's actually what we're going to do. We're going to take a solution where we find a coefficient where the c is positive. It's not going to be for the basic components, because those are always 0. But for a non-basic component, maybe there's one where the c coefficient in front is positive. And in fact, in this case, both of the non-basic coefficients are positive. But let's just work with the first coefficient. Let's do that one. Well, what happens is that if you increase x1, then a positive x1 times positive c1, that's going to make the overall objective function positive. And so the more and more I increase x1, the more and more the overall objective function goes up. But of course, I can't just willy-nilly increase the x1. I have to ensure that I'm maintaining feasibility, that I'm satisfying all the constraints. And so what's going to happen is I'm going to increase the x1 component, precisely because there's a positive c1 coefficient in front to make the overall objective function go up. But I'm going to compensate to maintain these feasibility constraints. I'm going to compensate by changing and messing with the basic x components, x3, x4, and x5. But remember, it's okay to mess with these no matter what happens to x3, x4, x5. The coefficients in front are 0, and so that's not going to change the overall objective function. So I'm going to increase this, and I'm going to get help from this booster variable that I'm boosting x1 because the coefficient in front is positive, and that's going to boost the overall objective function. But I'm going to compensate by changing these, but it's not going to hurt me. So I get help here for free, but it doesn't cost me anything because the C3, 4, and 5 don't hurt me because they're all zeros. That's the strategy. So here's what we're going to do. We're going to take a new solution. Let's call it x prime. And it's going to consist of, well, the components. So let me just label them: x1 prime, x2 prime, x3 prime, x4 prime, and an x5 prime. And I don't know what it's going to be yet, but I'm going to determine it component by component. So especially what I want is I'm going to focus on x1 prime. Let's look at x1 prime. This is what I'm going to call the booster variable. And why? It's because there was a coefficient in front of the first coefficient, c1, was positive, and so therefore when you increase x1, that's going to make the overall objective function go up. Now I could have done the same thing for c2, by the way. I'm just arbitrarily picking c1 right now. I could have done this for c2, but I'm just not. I'm picking c1 arbitrarily. Well, later on we're going to find that there's a strategic way to choose which one, but as long as you take a coefficient, a non-basic coefficient c, which is positive, and we're going to boost the associated variable. Now it could be the case that there's no non-basic coefficient, so amongst the cn's, maybe they're all, maybe cn is less than or equal to 0. All the components of cn are not positive. That's a possibility, but in that case, as it turns out, then that must mean that the solution we already have is the best possible solution. I'll expand on that in a later video, but that's not the case that we're in right now. So that's not the case. What we have is there is at least one component of C which is positive. In fact, there's multiple components, non-basic components, which are positive, and so we're picking the first one arbitrarily. So the associated variable here, we're calling the booster variable, and I'll call it T, just to indicate that it's special. Now, in the original solution, the original basic feasible solution, the second component was 0. In other words, so all the non-basic components were 0. Here, we're going to take one non-basic component to be the special one, the booster variable. All the other non-basic components will remain at 0, though. And in this case, there's only one other non-basic component, that's x2 prime. So x2 prime, I'm going to keep at 0, just like the original solution had a 0 for all the non-basic components. Here, it's all the non-basic components except for the special one. And in this case, there's only two components, so it's just there's one special component and one not special non-basic component. Now, we still haven't determined the basic components yet. And by the way, I haven't even figured out what the special booster variable is supposed to be yet. But we're just indicating that it's special by calling it T right now. So we still need to figure out what that is. But we'll get there in just a moment. But here's what we want. What's going to happen is that we're going to determine what these three components are in terms of the booster variable. That doesn't mean we know what the booster variable is yet. That just means that once we do, then we'll know all the variables. So here's how that works. So 6, 10, 4, that's our vector B. That's equal to the matrix A times x prime. I need this to be true, okay? No matter what, I need this to be a feasible solution, and so in particular, I need it to satisfy all these constraints, this x prime. So what this means is that 1, 2, minus 1 times x1 prime plus 1, 1, 1 times x2 prime plus the rest are actually all basic variables. What I've done so far, it just so happens that the non-basic components come in order, and then the basic components come in order, and they all come in order 1, 2, 3, 4, 5. But in general, I'm writing down the non-basic components, x1, x2, and now I'm going to write down the basic components all at once. The rest is going to be the identity matrix times the basic components of x. And so remember, this is because we're in canonical form, and so therefore the associated columns that are associated to the basic components form an identity matrix. And so that's why we can put this identity matrix here. So this is just taking the matrix multiplication of A times x prime, and we get this. And remember, x1 prime is our special variable. It's our booster variable that we're calling t. So this becomes t times 1, 2, minus 1. X2 prime is one of the many non-basic components, which were not the special one. In this case, again, there's only this one. So if this is 0, so this goes away. This term goes away because this is 0. This is 0, so this goes away. And this is the identity matrix times this vector, so this just becomes this vector, so xb prime. And this is equal to 6, 10, 4. That's what we need to have happen in order to satisfy the constraints. So what we get is t times sorry, let me just write it up top here. What we get is t times 1, 2, minus 1 plus x3 prime, x4 prime, x5 prime equals 6, 10, 4. That's what we need to have happen. Or in other words, what we get is x3 prime, x4 prime, x5 prime equals 6, 10, 4 minus t times 1, 2, minus 1. Or, as you can see, I can rewrite this. This is x3 prime. This is just compact vector notation for 3 constraints. x3 prime equals 6 minus t. x4 prime equals 10 minus 2t. And an x5 prime equals 4 plus t. And so this is what just happened, is that we still don't know what we want this booster variable t to be yet, but what we do know is that once we determine t, the basic variables of this new vector x prime, they are parameterized by t. Everything is in terms of t here. So once I know t, then I'll know x3 prime, x4 prime, and x5 prime. So I'll know the basic variables. Okay, so now, and by the way, the reason that we were able to figure that out is by this constraint. Enforcing these matrix constraints allowed us to parameterize x3 prime, x4 prime, x5 prime. But these are not the only constraints that we need to satisfy. We also need to satisfy the non-negativity constraints. Now, remember, what happens in this new solution is that we look at all the non-basic components and we say one of them is going to be the special component. In this case, we said x1 prime because the associated coefficient, c1, was positive. For all the other non-basic components, they all stay at 0. So for the non-basic components, do we maintain non-negativity? So let's take a look at the non-basic components. Well, one of them is t, and the others are all 0. And t, what's going to happen is t is the booster variable. We're going to increase it. It started at 0. Our original solution, all the non-basic components were 0, but now we're picking a special one and boosting it. So it's going to go above 0, so it's positive, and then all the rest stay at 0. So this will certainly be greater than or equal to 0, because I just said why. And so now all we need to worry about is the basic components. So I need to worry about, is it true that the basic components are greater than or equal to 0? Well, what are the basic components? The basic components are parameterized by this variable t here. They occur over here. So what I need is for this to be greater than or equal to 0, this to be greater than or equal to 0, and this to be greater than or equal to 0. Or in other words, I can rewrite these things. This says that t is less than or equal to 6. This says if I solve for t, move the 2t to the other side and divide by 2, this says that t is less than or equal to 5. And this one says t is greater than or equal to minus 4. This third one. So what just happened is we put constraints on t. Remember, t is the variable that we're boosting. It's x1 prime. It's the booster variable. So the more that you boost it, the larger and larger the objective function is going to get, because the associated coefficient in front is positive. So, make t bigger, you make the overall objective function bigger. but we can't make it arbitrarily big. That's what these constraints are saying. We just constrained t. T has to be less than or equal to 6, it has to be less than or equal to 5, and it has to be greater than or equal to negative 4. Well, okay, it was, being greater than or equal to negative 4 is not a constraint at all. It was already going to be positive, so it's the fact that it has to be greater than or equal to negative 4, this doesn't matter. These two do matter, though. But, in fact, one is more restrictive than the other, and the one that's most restrictive is t less than or equal to 5. So this is the most restrictive constraint, and so we can only increase t so much, but the more you increase it, the better your objective function is. So let's increase it as much as we possibly can, which is to say take t equal to 5. And so that's what we'll do. And so now we've just determined what t is. We determined it thanks to the non-negativity constraints. The non-negativity constraints here allowed us to determine that the harshest restriction on t was that it had to be less than or equal to 5, so boost it as much as you can, take it to be 5 exactly. And now that we figured out what t is, remember we parameterized the basic solutions, the basic components in terms of t, thanks to the matrix constraints. And so because we've parameterized them, now we know all the basic components. And necessarily the basic components here, xb prime, will be greater than or equal to 0. This will necessarily be true precisely by how we just chose t. T was constrained in these ways, so when you choose t to satisfy these constraints, then it satisfies the non-negativity constraints. Okay, and so we just figured out what this vector needs to be. The first component is our special booster component, and we just figured out how much we're able to boost by. 5. That's what the first component is. x1 prime is t, and t is 5. Okay, x2 prime was the other non-basic component, but it wasn't the special one, so that still stays at 0. And now the rest are basic components, and so we've parameterized the basic components in terms of t, and t is 5. So x3 prime is 6 minus 5. Which is 1. X4 prime is 10 minus 2 times 5. 10 minus 10 is 0. And x5 prime is 4 plus 5 is 9. And so that is our new solution. And when you plug this new solution into your objective function, so it necessarily satisfies all the constraints, and that we can plug it in. And when you plug it in, well, what happens is that you get C1 times 5 plus C2 times 0 plus C3 times 1 plus C4 times 0 plus C5 times 9. And everything will stay at 0, either because it was a basic variable, and for basic variables the C coefficients are 0, just as we said originally. That part still hasn't changed. But for the non-basic components, the x's are still zeros except for the special one. So this is still 0, but there's a special component now, and that's the first component. And that was because the C1 was a 2, and we got 2 times as much as we could possibly boost this booster variable by, which was 5. And so now we get 10 overall. And so that is the value of our objective function, which is certainly an improvement over the 0 that we originally had. And that's how this process works. There's a few things to mention, though. This always works, and I'm sorry, I'm losing my train of thought a bit. I'm trying to think of what order I want to say things in. I think it's important to note that. Sorry about this. I wish I knew what I wanted to say here. There's one special variable. That special variable is t. That allowed us to boost. But if we take a look here, what happened is that there was a component. Okay, so this is what I want to say, I guess. There was a component which was positive before. It was 10, and now it went to 0. It's no coincidence that this became 0. It's exactly because the corresponding constraint, this was the constraint, this fourth constraint here, so component 1, 2, 3, 4, it was the fourth component here from the basic solutions of the non-negativity constraints, this was the harsh restriction. This was the harshest restriction. This was the thing that was responsible for making t be less than or equal to 5. And so since that was the harshest restriction, when you boost t to be as much as it can, it bumps into the edge case of t being equal to 5, and so that forces this x4 prime all the way down to 0, because the bigger and bigger you make t, the smaller and smaller x4 prime gets, and t had to be less than or equal to 5, so when it's exactly 5, this went all the way down to 0. If you made t any more, this would have been negative, and it would have violated non-negativity. So therefore, it's no coincidence that this component, this fourth component, became 0. It's exactly because it was the harshest constraint. Another thing that happened is that there was a component which was originally 0, and now it's positive. And in general, it just has a potential to be positive. And that's because it was the booster variable. So what happens is that we had a basis 3, 4, 5, but actually now there's a new basis, and that is components. What happens is the harshest constraint, that basic component, gets dropped out. So we keep the 3 and the 5, but we lose the 4. The 4 was the other basic component here, but we lose that one because that was the constraint that was the harshest, and the most imposing. But we add in a new component which was positive, and that was the booster variable, which was index 1. And so now we have this new basis, 1, 3, 5, and you can actually verify that in fact this necessarily is a basis. And in general, for this process, this will be a basis. So the basis comes from exchanging the harshest constraint for the booster variable. Exchange those two things and you get a new basis. And so what happens is now we can put our linear program in canonical form for this basis, and then we can reiterate this entire process. And we know that we can do this because we just said in the previous video that we can always put our linear programs in canonical form for any basis. And so here's a new basis, which get results from how I just described, exchanging the harshest constraint for the booster variable, and the booster variable index, I guess. And now we can put it in canonical form for that basis, and then you can iterate this process. And actually, that's actually what the simplex algorithm does in general. And that's what I mentioned when I said that the canonical forms were a subroutine of the simplex algorithm. Put it in canonical form, find a coefficient that's positive, boost the variable as much as you can, and then develop your new basis, find your new basis, put it in canonical form for that, and do it all over again. And that's how you find better and better solutions, and that's basically what the simplex algorithm is. So in the next video, we're actually going to formalize that process. Yeah, actually that's everything I had wanted to say for this video, I guess. So what we needed to start out with a basic feasible solution in order to get this whole process, to catalyze this process and let the chain reaction go off. But once you start with a basic feasible solution, then you can generate more and more solutions that are progressively better and better. Yeah, that's how it works. So step 1, get your find your booster variable. Step 2, parameterize your basic variables in terms of your booster variable. That parameterization comes as a result of these matrix constraints. And then step 3, find out how much you're able to boost this booster variable by as a result of the non-negativity constraints. And now you've incorporated all the constraints, so the resulting answer vector is going to be satisfying all the constraints, so it will be feasible and it will be better because you're boosting t by some amount, and that's what this process is. So this, like I just said, this is basically what the simplex algorithm is, and you just iterate this over and over. And so we'll formalize that in the next video, and that'll basically get us to the simplex algorithm. But that's it for this video. So thanks for watching.